You've seen horizontal asymptotes before in functions like 1 over x. Usually, we would draw a horizontal line at a particular y value, like in this case, y equals 0, and we would say that this curve has a horizontal asymptote at y equals 0 if, as the x values get larger, the y values get closer and closer and closer to that number without ever reaching it. So let's write that down as our initial definition. It's often notated this way. We'd say a function has a horizontal asymptote at y equals k, where k is just some specific number, like y equals 0. We'd say the function has an asymptote at that value if, as x approaches infinity, y is approaching k. We could say approaching infinity or negative infinity. But it might not be that clear. What do we mean when we say approaching infinity? Or what does it mean when we say approaching k? So when we say approaching infinity, what we usually mean is that the x values are getting larger and larger and larger without ever hitting an upper boundary where they're never going to get any larger than that. Because you could imagine getting larger and larger and larger, like 9, 9.9, 9.99, 9.999. Those values are still getting larger, but they're never becoming larger than 10. So sometimes this is phrased as growing without bound. And so if the x values are getting larger and larger and larger without ever hitting an upper bound, the y values are getting closer and closer and closer to k. In just a second, we'll see why it's not actually as clear as it seems to say that y values are getting closer to a number. But right now, let's just see how that definition fits the example we know. So here, you see the x values are getting larger and larger without bound. They're approaching infinity. What happens to the y values? Let's plug them in. So we have 1 over 1 is 1. If I plug in 2, I have a y value of a half. If I plug in 10, I have a y value of a tenth. And if I plug in 100, I have a y value of a hundredth. And you can see those points plotted here. Here's 1, 1, 2, 1 half, 10, 1 tenth. So as x is approaching infinity in this direction, the y values get closer and closer to 0 without ever reaching it. So let's write y approaches 0 right there. Okay, I'm going to show you 3 examples that are a little bit less clear to see whether or not they fit this definition. And that's going to cause us to try and come up with another way of thinking about it. And you'll have to wait until calculus or maybe even a class called real analysis to get the full formal way of thinking about this, which is called an epsilon delta proof of a limit. But for now, let's look at the examples. So here I've got y equals 2 plus 1 over x. I've got 2 plus 1 over x plus this sine function. And I've got sine x over x. And in each of these cases, I want you to ask yourself, as x approaches infinity, is y approaching a particular number that you would call the horizontal asymptote? So here are the y values getting closer and closer to 2. Here are they getting closer and closer to 2. Here are the y values getting closer and closer to 0. So decide right now, just your own intuition, what you think. So in this case, as x gets larger, this entire term can become as small as we might ever want it to be. This term is approaching 0, which means that the y values must be approaching 2, because the thing that we're adding on to 2 is getting smaller and smaller towards 0. So a good way of thinking about this is you could say, are the y values approaching 2? Well, we could say, is it possible to get all of the y values as close to 2 as we might ever want just by making x larger? So you could say, all right, what if I want all the y values to be within 1/100th of 2? Well, we could do that just by making x larger than 100. What if 1/100th isn't very close to the asymptote? We could say, what if we want all the y values to be within 1/1000th of 2? Well, that's true as long as x is larger than 1000. So you can get the y values of your graph as close to the asymptote as you want just by making x larger. So that's going to be our kind of informal, new definition, more nuanced definition of what it means to have a horizontal asymptote. We're going to think about it in terms of being able to get all of the y values arbitrarily close to the y value that we're interested in. So here we're going to say, yes, it does have a horizontal asymptote at y equals 2. Okay, what about this case? So here, this part of the function is the same as what we just looked at, only now we're adding this other sine function. Remember, a sine function oscillates between -1 and +1. And this one's been vertically scaled, so it's a little bit shorter. So this one's oscillating between -1/50th and +1/50th. And that's what's adding all of these little wiggles here that you might notice. Well, let's ask the same question. As x approaches infinity, are the y values approaching 2? And hopefully here your intuition says no, because the y values are continuing to get closer and then further and then closer and then further as we have these oscillations. So for now, let's not think about it more precisely or more carefully than that. For now, let's just say no. There is no horizontal asymptote. And let's look at this one first to contrast. So because we said no here because of the wiggles, we might say no down here because of the wiggles as well. But first, let's think about why does this equation even make this shape. So sine x, we said, oscillates between +1 and -1. So you could imagine sine x without dividing it by anything. If we divide sine x by 2, now instead of alternating between 1 and -1, we've squished it vertically. So it's oscillating between a half and -1/2. If we divided it by 10, we would have squished it by a factor of 10. So now it's oscillating between 1/10 and -1/10. So you can think about this x here as being a vertical scale factor. It's just squishing the sine graph by more and more and more the further right you go. And hopefully it's clear from this picture that that description makes sense, because here I start off with a sine function that looks just like a regular one, but then as x gets larger, the peaks and the valleys are becoming compressed because I'm scaling them down by larger values. Okay, so the question is, as x gets larger, are the y values getting closer and closer to 0? You might think, no, they're not. What's actually happening is we hit a y value of 0 over and over and over again, and then no matter how far we get along this graph, the y values are always going to have places where they get larger away from 0, or they get smaller away from 0. And so it seems ridiculous to say that the y values are approaching 0 if they're also always going away from 0. So we're not approaching anything. We're going away and coming back and going away and coming back. Okay, that's why the usual way that you describe this in pre-calculus is not good enough. So let me say what a mathematician might give you as a counter-argument. They might say, well, look, let's take a look at the peaks of each of these waves. So let's look at the highest point that sine ever reaches. This dashed line actually moves, all the peaks lie on this dashed line. And this dashed line is actually the function y equals 1 over x. And you can see that by thinking about the largest value sine could ever be. Remember, sine by itself can't be larger than 1. So that means no matter what x is, the y value can't ever be larger than 1 divided by x. And so that's why you see that as x increases, the largest y values at these peaks are still not larger than the 1 over x function. So now we're in trouble because we said way back at the beginning of the video that the y values of 1 over x are getting closer and closer to 0. So it feels now like maybe it should be okay to say that even though the y values of this function oscillate, the oscillations are getting smaller and smaller. So all of the y values, even though they're oscillating, those oscillations are still getting closer and closer and closer to this y equals 0 number. Okay, let's try now and write down our more nuanced idea. I said it verbally a second ago, but let's write it now in English so that we can see it written down. We said something like this. Y approaches k means something like you can get the y values as close to k as you want them to be just by making x larger. So let's think about that idea as applied to this graph. Okay, so what if I want all of the y values of our function to be, within 1/1000th of 0? I can make that happen just by making x large enough. So I could make that happen just by making sure x is larger than 1,000. And now I know that if x is larger than 1,000, all the y values in the graph to the right of that are going to be within 1/1000th of 0. And I could choose an even smaller window here. I could say 1/1,000,000th or 1/1,000,000,000th or 1/1,000,000,000,000th. So we can get all of the y values arbitrarily close to 0 just by making x bigger. So that's our new, more nuanced idea. And I said earlier that this is called the formal way of writing this idea down would be called an epsilon delta proof of a limit. And you can look up videos on that if you want. But I think I just wanted to expose you to the idea that it's not that clear what it would even mean to say that y values approach a number, and to suggest a slightly more precise way of thinking about it. Okay, so what takeaways can we have from this video for our class? For our class, we'll still use this language. We'll still say as x approaches infinity, y approaches k, and you can usually think about it as y values are getting closer and closer to k, but never reaching it. It's important to be able to think about the asymptote happening at a particular y value, and then also to realize that there is this more nuanced picture in your future that you'll be thinking about. Okay, come for the next video where we'll talk about vertical asymptotes.